Okay, in the next problem, we have 1969 AB4, and the number of bacteria in the culture at any time t is given by that. Notice that this is the number of bacteria. This is not an equation for the rate of change. We want to find the largest number and smallest number of bacteria in the culture during the interval. First thing I want to say is note the closed interval. Even though the terminology in part A does not say absolute, min, and max, because we're dealing with a closed interval and we're asked to find the largest, this is really referring to the absolute min and max. So the largest and smallest values in A then refer to absolute, max, and min respectively. And to find them, we'll have to test the original function at critical values and endpoints. Alright, so to do this, we need to find the first derivative. So the original function is 1000 times 25 plus t e to the negative t over 20 quantity. And we're going to, what I would suggest doing then is multiplying that out first. And when we take the derivative, the derivative of 25,000 will just become 0. After that, we're going to have a product rule. This problem, by the way, is not a volume and area problem. Although it's thrown in here, it is an application of derivatives that works with exponentials. So y prime is 1 d2. Seeing that the derivative of 25,000 is 0, we won't even worry about that. We're calling 1 the first function 1000t, the second function e to the negative t over 20, so 1. Now the derivative of e to the negative t over 20 is e to the negative t over 20 times the derivative of negative t over 20, which is negative 1/20th. So that gives us 1 d2 plus 2, and d1 would just be 1000. Now one of the reasons I like to include this problem is because it shows the factoring that goes on with this type of problem. So we have a common factor of 1000 and e to the negative t over 20 in each term. And since that's an exponential, that's never 0. And that leaves negative t over 20 plus 1. And that whole expression is only equal to 0 when t over 20 is equal to 1 or when t is equal to 20. So what we need to do, that's our only critical value in there. What we need to do now is to test the original function at the endpoints and the critical value. So we're going to look for y of 0, y of 20, and y of 100. At 0, you should find that the function is equal to 25,000. At 20, then negative 20 over 20 is going to give you a negative 1. So it's going to be 20 over e, so it's 25,000. Or we'll just write that as 1,000 times 25 plus 20 over e. And the second, or the last one, evaluated at 100, that gives you 1,000 times 25 plus 100 over e to the fifth. And so if you're looking for the largest, we just have to make a judgment. But all of them have 25,000 minimum. And the only difference is the 20 over e or the 100 over e to the fifth. At 20 over e, if we roughly say that e is about 3, then 20 over e is somewhere between 6 and 7. If on the other hand, e to the fifth is going to be something like 243, so 100 over 243 would be about a half. So definitely the middle number, y of 20, is the maximum, and y of 0 is the minimum. So it has to find the largest number and the smallest number of bacteria in the culture during the interval. So the smallest number is 25,000, the largest is 1,000 times 25 plus 20 over e quantity. Alright, and we'll pick up part B in the next video.